Hello and welcome. My name is Pawel Dlotko, and today I'm going to tell you about the game of trees, which I have invented. The purpose of the game of trees is, first of all, to have fun, but also for you to understand some basic concepts of the graph theory, the concepts of tree, of a general graph, as well as the concept of a path in a graph. Those are concepts from discrete mathematics, which are kind of useful in many different levels of life. So it's always good to get to know them. Let's take a look at the folder that contains the game. So you should find a bunch of subfolders called anything between 4 edges to 11 edges, and you should find a PDF. This PDF contains the basic introduction to the concept of graphs, contains the introduction to the trees, as well as the general description of the game, the description how you should play the game, and what are the general rules. And that is something that we are going to cover in brief in this quick tutorial. So the level of difficulties is really proportional to the number of edges you have in your tree. The rule of thumb is that the fewer edges, the easier the constructions are, although there are exceptions. Within the collection of trees of a given number of edges, for instance, 7 edges, there are trees which are easier to reconstruct, there are trees which are more difficult to reconstruct. So if we enter each of those folders, for instance, 7 edges, this folder do contain a list of all possible trees having 7 edges. You can see the plots of them. Once you click at any of the PNGs, those plots are nothing more but the answers to the game. The questions can be found in only text file available in the folder. So let us take a look at the text file. Well, here it is. It contains 23 lines. It means that there are 23 different trees of the length having 7 edges of the length. 7. And those trees can be reconstructed just by looking at the vector containing the lengths of the different paths in the trees. Let me pick an example which is not too easy, not too difficult. Perhaps this one, which is the tree number 15. It contains 8 vertices, 7 edges, 8 paths of a length 2, 8 paths of the length 3, 4 paths of the length 4, and 1 path of a length 5. So we have this vector of numbers 8, 7, 8, 8, 4, 1 copied in our piece of paper. Just to remind you, this 8 means that we have 8 vertices, 7 edges, 8 paths of the length 2, 8 paths of the length 3, 4 paths of the length 4, and 1 path of the length 5. And we know from the description of the game that there is one and only one tree that have such a number of paths of a different length. In order to build it, I will simply use matches. And for the purpose of this demonstration, I just have enumerated them. So it will be easier for us to follow what's going on. In general, you do not need this enumeration. And there are different strategies you can apply in order to build such a tree. And particular strategy which I'm using is to start from the longest path in the tree, which in this case is the path of the length 5. And I can simply build it by putting those matches together. Well, that already is a tree that contains 5 edges, 6 vertices. I have 2 edges that I need to attach to the structure, but right now what we have is a tree that have 1 path of the length 5. It also has 2 paths of the length 4, namely the first path is 1, 2, 3, and 4, and the second one is a path consisting of edges 2, 3, 4, and 5. So I need to use those 2 matches in order to add additional 2 paths of the length 4. So the question is, where can I attach this edge number 6? Well, I cannot do it over here, because then my graph would have a path of the length 6, which we know that it do not have. I cannot attach it over here, because then I would have another path of the length 5, namely consisting of edges 1, 2, 3, 4, and 6. We know that we only have one of them, so I cannot attach this edge over here. Well, how about right here? Well, that would give us an additional path of the length 4, in addition to 2 that we already have. This path will consist of edges 1, 2, 3, and 6. Okay, let us leave this guy where it is. So far, so good. Question, where can I put this guy? Obviously, I cannot put it over here. I cannot put it over there because of the same reason as for the edge number 6. Also, I cannot put it over here because then we would have another path of the length 5 consisting of edges 1, 2, 3, 6, and 7. So that is explicitly forbidden. So how about we put it right here? Let's see what we have. So we have number of paths of the length 5 is 1, because there is only one path of the length 5 consisting of vertices 1, 2, 3, 4, and 5. That is correct. How many paths of the length 4 do we have? Well, we have, let's count them. So we have a path consisting of 1, 2, 3, and 4, that's 1. 2, 3, 4, and 5, that's 2. 1, 2, 3, and 7, that's 3. 1, 2, 3, and 6, that's 4. So far, so good. Let us see how many paths of the length 3 do we have. So let's do another counting. We have a path consisting of 1, 2, and 3, that's 1. 1, 2, 3, and 7, that's 2. 2, 3, and 4, that's 3. 2, 3, and 6, that's 4. And then we can just carry on. So we have 3, 4, and 5. That's the fifth path. The sixth path will be the 6, 4, and 5. That's the path number 6. And the path number 7 will be 6, 4, and 7, 4, and 5 is number 6, and 6, 4, and 5 is number 7. That gives us 7 paths of the length 3. However, as we can see over here, we are supposed to have 8 of them. We only have 7. So this tree is really not represented by that vector of the path length. It means that some of our choice was bad. So let's try to correct it. And try to correct it by actually making another choice for the edge number 7. Obviously, like, I cannot put it over here, I cannot put it over there. And symmetrically, I cannot put it over here, and I cannot put it over there for exactly the same reason. So the only, one and only place I can put it is over here. Okay, so let's do the counting once again. There is, as it used to be, only one path of the length 5. We know that. As for the length 4, so we have 1, 2, 3, and 4, that's number 1. 2, 3, 4, and 5, that's number 2. But also we have 1, 2, 3, and 6, that's number 3. And 5, 4, 3, and 7, that's number 4. So we have 4 of them. Okay, that's exactly as we used to have. The question is, will we have 8 paths of the length 3? Well, let's do the calculations. Let me actually compute all the paths along the main backbone first. So 1, 2, and 3, that's number 1. 2, 3, and 4, that's number 2. 3, 4, and 5, that's number 3. And then let's do the branches. So we have 1, 2, and 7, that's number 4. We can go from that side, so we have 4, 3, and 7, that's number 5. And right now we use all the possibilities, almost all the possibilities with the main branch and number 7. Let's use number 6, so we have 2, 3, and 6, that's number 6. 5, 4, and 6, that's number 7. And where is the 8th path? Where? Here it is. 7, 3, and 4, and 6. That's the path number 8. So indeed we have the 8 paths of the length 3. Let us compute the number of paths of the length 2. We are expecting 8 of them. And let me do the main backbone. So 1, 2, this is number 1. 2, 3 is number 2. 3, 4 is number 3. 4, 5 is number 4. And let's do the branches. 2, 7, that's number 5, 7, 3, that's number 6, 3, 6 is number 7, and 6, 4 is number 8. So indeed, we have 8 paths of the length. 2, obviously we use 7 matches, and they have, so we have 7 paths of the length 1. And let's count the vertices. So we have one vertex over here, vertex number 2, vertex number 3, vertex number 4, vertex number 5, vertex number 6, vertex number 7, and vertex number 8. So everything plays off. If you remember, that was a tree number 15 in our file. So what we need to do in order to check if this construction is correct is to go to that precisely that file, tree number 15 with 7 edges, and we'll get that picture. Well, if you look at this, it's not precisely what we have over here, but I can actually move it around so that I get what I need. I just put this branch a little bit below that branch, and that thing goes a little bit higher, and that thing goes perpendicular. So I didn't change the connectivity, I just changed the layout, and well, we get the same graph as we have over here. It means that we solve the task perfectly. Okay, well, let us do one more example perhaps. Why don't we take the tree number 18? That actually contains a few longer paths. So let me copy this vector of numbers. So we have 8, 7, 7. 6, 5, 2, 1. Okay. So we know that we have 8 vertices, 7 edges, 7 path of the length 2, 6 path of the length 3, 5 path of the length 4, 2 path of the length 5, and 1 path of the length 6. Once again, we can use our matches to actually build up the trees, and I will just imply my standard strategy of building the longest path first. So I want to build a path of the length 6. Well, here it comes. Number 3, number 4, number 5, and number 6. So that's the main part. That's something I may call the backbone of my tree. I'll make it a little curvy in order to fit it into the screen. So we have one path of the length 6. How many paths of the length 5 do we have already without adding this additional edge? Well, we have 2 of them. One of them consists of edges 1, 2, 3, 4, and 5. And the other one consists of edges 2, 3, 4, 5, and 6. So already by building the backbone, we know that we satisfy those 2 conditions. Now we want to add edge number 7 so that we don't destroy what we have already. It means that we cannot add it over here in one of the endpoints, because then we'll create a path of the length 7. We cannot add it in over here, because it will create an additional path of the length 5. In this case, it will be 7, 2, 3, 4, 5, 6. Likewise, we cannot add it over here for exactly the same reason. So, essentially, thanks to the symmetry, well, we can add it over here, and over here. And, adding it over here and adding it over there is exactly the same, because, that thing is symmetric. So let me add it over here first, and let us check if the number of paths in that graph which we just have created agrees with that vector. Right. So we know that we have one path of the length 5, one path of the length 6. The number of paths of the length 5. Well, if we add it over here, what will happen is we'll have an additional path of the length 5, namely consisting of 7, 3, 4, 5, and 6. So instead of having the two paths of the length 5 coming from the backbone, we'll have 3 of them because of this additional one. So I cannot put an edge over here, I cannot put an edge over there. Obviously we know that I cannot put it over here, neither over here nor over here. So the one and only possibility is to put it in the middle. Right? By doing so, we'll have an additional path of the length 4 over here, an additional path of the length 4 over there, but we will not increase the number of paths of the length 5. Okay? So we know already that this tree contains one path of the length 6, two paths of the length 5. Let's count the number of paths of the length 4. We expect 5 of them. So first let me do the backbone. The path 1, 2, 3, 4 is number 1, 2, 3, 4, 5 is number 2, 3, 4, 5, 6 is number 3. In addition to this, we have path 1, 2, 3, and 7, that's number 4. Also 6, 5, 4, and 7, that's number 5. And those are the only paths of the length 4 we have. And we have 5 of them. Okay, we can count the number of paths of the length 3 right now, and we expect 6 of them. Let's see how many of them do we have indeed. So we have a path 1, 2, and 3, that's 1. 2, 3, and 4, that's 2. 2, 3, and 7, that's 3. 3, 4, and 5, that's 4. 4, 5, and 6, this is 5. And I have one path missing, so maybe let me do the counting once more. 1, 2, and 3, this is number 1. 2, 3, and 4, this is number 2. 2, 3, and 7, this is number 3. 3, 4, and 5, this is number 4. 7, 4, and 5, this is number 5. And that was the missing one previously, and 4, 5, and 7, that's number 6. So this time we have 6 paths of the length 3. And you know, the mistake which I just made really tells you how careful you need to be in order not to miss any of those paths. Okay, let's count the number of paths of the length 2. 1 and 2, that's number 1. 2 and 3, that's number 2. 3 and 4, that's number 3. 3 and 7, it's number 4. 7 and 4 is number 5. 4 and 5 is number 6. 5 and 6 is number 7. So indeed, we have 7 paths of the length 2. Obviously, we have 7 matches, 7 edges, and we have 8 vertices. Well, it's really a consequence of the fact that this graph is connected, but let us point it out explicitly. So this is vertex 1, vertex 2, vertex 3, vertex 4, vertex 5, vertex 6, vertex 7, and vertex 8 at the end. So this is the tree we constructed. We know that this is the tree number 19. So we know that, well, we made a calculation of the number of paths. Let us take a look at the tree number 19. And it should be somewhere here. Here it is. So that's the tree number 19. And this is what we have. And well, what I can do is, well, without changing connectivity, I can put an edge number 7 up here, and I can make, you know, those things a little curvy. Now it's just a different way of drawing exactly the same tree. And as you can see, the thing which we just created is exactly the same as the thing that we needed to create. So now that's how you can play the game of trees. You need to do the counting very carefully, and then once you think that everything agree, you just check the answer. Remember that you need to adjust your graph a little bit. You can do it without changing connectivity of your graph. For instance, moving a vertex, moving an edge like this, won't change the connectivity. This graph, this is just a different drawing of exactly the same graph. And you know, once you check and everything is fine, and, you know, the graph is exactly as it should be, it means that you did the reconstruction well, and then you can go ahead and make another one. I hope you all enjoyed the game. Have fun. If you have any questions, any comments, please let me know. Have fun, take care, and enjoy.